FlowCamp is a European training network for researchers in the field of next-generation redox flow batteries. It consists of the work of 15 PhD students on 3 different redox flow battery systems: organic flow batteries, zinc air, and hydrogen bromine.
Hello, I am Diego Milian from Guatemala. I am a PhD student at the Laboratory of Rheology and Processes in Grenoble, France. I am part of the FlowCamp project and I am working with the zinc air redox flow battery group. My PhD thesis is about the formulation and rheological characterization of zinc slurries as anode electrolytes. Zinc offers a high energy density storage medium. To make a fluid out of a metal, the zinc particles are fluidized in the form of slurries that can be pumped into the battery in order to be discharged or charged. In my research, I use rheology, which in few words is the study of the formation and flow of matter, as a tool to study how a given material will flow throughout the redox flow battery cell. In a zinc slurry air redox flow battery, zinc slurries work as an electrode and as an electrolyte at the same time. The zinc particles are usually dispersed in alkaline medium with the aid of gelling agents. These gelling agents help to improve the flow behavior as well as the stability of the suspension, which show a complex fluid behavior. Viscosity is a key process factor as it is directly proportional to pressure losses in the system. For example, if slurries possess a high viscosity, more energy is needed to make them flow as the resistance to flow in the system will be greater. Once a material shows a satisfactory stability and viscosity, it will be tested electrochemically in order to analyze its performance. One of our interesting results consists in modifying flow behavior of slurries by using a combination of different gelling agents, even in harsh alkaline conditions used for zinc air chemistry. What is also interesting is the trade-off between stability and performance, because higher viscosity systems lead to longer shelf life, but on the other hand, the increase in viscosity affects conductivity and feasibility of the process due to higher pressure drops. Therefore, one needs to be aware of the compromise between stability and performance. The understanding of material properties to tailor rheological behavior in semi-solid flow cells can bring a significant change to the energy market. So what is important is the know-how to adapt specific active materials to a process by modifying their flow behavior, taking into account key rheological parameters and electrochemical performance. It is important to demonstrate the broad applications and importance of rheology when designing a process. This is even more important when dealing with such complex formulation as slurries, as viscosity tends to be higher. Upcoming work comprises flow visualization, which is a key step to understand the flow profile and velocity of a slurry in different flow channel geometries inside the cell, which are called flow fields. In parallel, as slurries are complex systems, it is important to identify interaction between all the components in the formulation at molecular level in order to predict long-term stability as well as unwanted side reactions.